My name is Darian Zimmerman. I attend the University of St. Thomas, and I'll be addressing the developing issue of using biofuels while conserving biodiversity. In the first article I took a look at, entitled Energy Sprawl versus Energy Efficiency, we are introduced to the concept of energy sprawl. This is the production of total quantity of energy produced per year and the land use intensity. The article described the need for energy conservation, appropriate siting, sustainable production means, and compensatory mitigation offsets. In my next article, Land Clearing and the Biofuel Carbon Dip, the high priority need for switching to low carbon fuels is pointed out due to the increasing energy use, climate change, and carbon dioxide emissions from fossil fuels. It also mentions the notion of carbon debt. This is the amount of CO2 released during the first 50 years of the biofuel production process while it starts off. In the third article of this project, we are shown that not only is the demand for energy escalating, but also the need for food. Because of this, the potential of using food-based biofuels is raising concerns. The current biofuel production competes for fertile land, increases fertilizer and pesticide pollution, and threatens biodiversity. The article also breaks up the production means into two major classes: monoculture crops that are grown on fertile soil, and waste biomass. There is also a potential for a third class stemming from production of high diversity mixtures of plants grown on low inputs of agriculturally degraded land. Next, I focus on the economic competitiveness of biofuels. It must be economical, producible in sufficient quantities to substantially impact the energy demands, and provide a net energy gain over the energy sources used to produce it. Expanding on the consequences of habitat loss, this article, Biofuels and Biodiversity, explains that essentially the rapid development of biofuel markets could accelerate and magnify the rate and extent of landscape change, which may potentially exacerbate the degradation and loss of habitat needed to support biodiversity. It continues to explore the various impacts of biofuel production on biodiversity. These impacts depend on the spatial extent and landscape patterns of the land requirements for biofuels, the biodiversity habitat value of the land that biofuel feedstocks would require, and any off-field impacts of biofuel production, including water demands and fertilizer and pesticide pollution. This diagram shows the many complex factors that drive the development and production of biofuels in the United States. The dominant contributing factors are shaded. Now this is where the corn comes in. I found that in 2014, 136.78 billion gallons of gasoline were consumed in the United States, and 2.5 billion gallons were consumed in Minnesota. Further, 2.8 gallons of ethanol can be produced by 1 bushel of corn. Ethanol has approximately 70% of the energy content of gasoline per unit of volume, so for every gallon of gasoline consumed, 1.4 gallons of ethanol would be needed to displace it. That's 3.5 billion gallons of ethanol needed and 1.25 billion bushels of corn that would be needed to produce Minnesota's ethanol demand. This is the GIS model I used to create various maps to get as much raw corn as Minnesota could produce in order to supply for the demand to make ethanol. Here I have 3 maps displayed. In the first, developed areas. The second is water throughout Minnesota, and third are areas that are too steep. Each of these pose a complication for corn production because corn cannot easily be grown in cities, bodies of water, or intensely steep areas of land. This map shows what I eliminated from the equation. You can see that I erased forested areas in order to find out where else corn could be grown if all areas of forest land was used. This is my final map displaying all of the areas in Minnesota that corn could be grown if there was no forest land. Only areas with cities, water, and steep land would be free of corn.